And let me introduce our speaker. We're very happy to have Oana Balmau here with us. Oana is an assistant professor at McGill University in Canada, and she's leading the Data Intensive Storage and Computer Systems Lab. Her research is similar to our interest as well here, right? So there's a lot of systems happening, but then there's a lot of interest in machine learning workloads, data science, and edge computing. Before McGill, Oana was a PhD student at University of Sydney with Willis Vanpool, and before that, she was at EPFL, where we also coincided when I was a graduate student at the time. So the floor is yours.
Thank you, Manas, for the introduction. It's really nice to be here and give this talk, especially as you said, we have very similar research interests. And I noticed that the name is similar as well. So when I picked it, I wanted to spell disks, and then I saw that you had very true. Similar. Yes. So there is definitely a connection there. So today I thought to tell you a bit about some of the more recent work on reducing space amplification in storage systems. So let's get started. So why would we care about space amplification? First of all, as we all know in this crowd, we are producing a lot of data, and this data is expected to grow exponentially. So what this means is that increasingly we need to be more careful in the way we use storage space, both volatile space and persistent storage space, especially in fast drives. Now, before I start to tell you a bit more about drives and everything, I thought I would just break down the title so we're all on the same page here. So today I want to talk about reducing space amplification in key value stores. Before I get to the reducing part, I want to tell you about the key value stores part and the space amplification part. So key value stores, quickly, they're very important components in big systems for handling unstructured data. So here by unstructured, I mean data that doesn't really fit in a predefined data model or a data schema. So we cannot a priori directly put it in a traditional relational database. So this is either because the schema hasn't been defined yet, or because the schema might change on the fly as applications evolve. The structure of a key value store is very similar to a dictionary. So we're storing key value pairs. The data items can have multiple sizes and multiple data types, ranging from integers to more complex types like videos or images. What these key value stores offer in speed and flexibility, they kind of trade off in complexity of the API. So we have a very simple API that basically allows ways to read, write, and range scan over the dataset. These key value stores are used a lot in industry. These are just a few examples of popular data stores, non-exhaustive list. For instance, at Nutanix, a company I am collaborating with right now and during my PhD, they're using RocksDB, a log structure merge key value store, to handle metadata for thousands of clients and something in the order of petabytes of storage capacity. Now, I'm not going to talk about LSMs today, but I do want to cover broadly what we find, what kinds of components we find in key value stores. So it's a very high level view, so that I can tell you where the space amplification comes from. So on persistent storage, normally we have the data, which can be in various formats. We can have files, object stores, etc. We don't really care about it in this talk. We just know that it's data. And here I added it's typically sorted so that we have the possibility to scan over it. Now, to be able to retrieve the data, we also need some metadata, which one of the most important parts of the metadata are the indexes that allow us to find different items in the data stores. So today we're going to focus on these two parts, the indexes and on the data. There are, of course, other optimizations that you are probably very familiar with in this group. So we have write buffers to be able to do writes quickly, for example, in LSMs. So we have read caches. We could have a write-ahead log or Bloom filters, and all of these things are great and very interesting. But for today, we're going to leave them out and just focus on indexes and the data that resides in persistent storage. So now that I gave you a bit of an overview, refresher on key value stores, I'd like to talk about space amplification. So the way I define space amplification very simply is the total space that's taken by the storage system divided by the amount of useful data. Typically, this is the data that is that we want to store because it's the most recent version of the data, or data that we still need in order to process a query that's ongoing. And typically this ratio is greater or equal to 1. You might wonder, when we talk about space amplification, why do we care? Kind of conventional wisdom is that storage is cheap and we can have a lot of it. So why would we care that we use a little bit extra to store all data every now and again? However, it turns out that in production systems, this is becoming a very important issue. So these are just two examples. And I actually saw, browsing the MiDAS page, that Seeing from Meta actually came to give a talk on space amplification in RocksDB. So this is very timely. It is indeed one of the points where they are trying to optimize. Another example is from Alibaba. So a recent paper from Sigmod, they claim that garbage collection tasks are run with the highest priority in order to prevent waste of space. And this is especially pressing when the datasets are stored on newer devices like NVMe SSDs. So why is this more pressing? Simply because these SSDs are much vaster than SSDs from, say, 10 years ago. So this graph is just a sketch of spec values of sequential write bandwidth for SSDs at different points in time. We see here in 2018 the transition to NVMe, Optane, and Optane drives, and we see a steep increase in bandwidth for writes. So it's an order of magnitude higher write bandwidth. And this means, since we have more and more data that we produce, that we can also accumulate a lot of items in a very short time, which contributes to this space amplification. So some of the main causes of space amplification are at the data level and at the metadata level. First, at the data level, if we want to run transactions on a consistent version of the data, typically, key value stores run the transactions under snapshot isolation. And I will talk a lot more about snapshot isolation in a few minutes. But this is a cause of a quite important space amplification. The second cause is that sometimes items might be logically deleted, but they are not physically removed from the data store. And Mano's group has very nice work on these deletion efficient LSMs, which is a very real and important problem that also contributes to space amplification. The third cause of space amplification, at this time, this is at the memory level, is the size of the indexes themselves. And here, this is a more nuanced point, because the index size could be small relative to the dataset size, depending on how large each item is. So this problem of space amplification for the indexes is especially tricky for very small items. And there are real production workloads, again, another meta study released a characterization of their workloads showing that a broad category have small items. So today I'm going to focus in the first part of the talk on this first cause of space amplification due to snapshot isolation. And then I will later briefly talk about some ongoing work on reducing space amplification for indexes. So this now I will start to get a bit more in the meat of the talk with the snapshot isolation part. So if there are any questions up to this point, I can take them now. Feel free to write in the chat or raise your hand. I think raising your hand would work since it's a relatively small group here.
All right. But yeah, feel free to jump in, everybody.
Yeah, I think I have a quick question.
Sure.
So in your clause 1, you say that you have older versions of data for transactions. So if I want to query on older data, is that data categorized as useful data or not useful data?
So here, that's a great question. Here it depends on how you keep the key value pairs, right? So for example, in time series, if your key is time, of course, old data is very important because we want to see trends. So that wouldn't be considered useless data. However, in say a system that is doing cluster management or tracking metadata, if we move a virtual disk from location A to location B, then the fact that it existed at some point, the disk existed at some point at location A might be considered useless data, and the new location B would be, say, the new value that's associated to the virtual disk location, right? So it really depends on the application.
Yeah, makes sense.
But that's a good point.
I have a quick follow-up on that. So essentially, so if we think about your key value store, right, and we said that you move disk from location B to A, so now the new value is A, for example, or B, whatever it is. So, however, now this happened and happened in a transactional manner, meaning that essentially you probably did more things, and they all have to be seen together as a transaction. And I'm sure you're going to talk about that, but I'm just setting the stage here. So essentially, if a query has come that requires the status of your cluster, right, and the query came at an earlier time before the transaction was completed, presumably the query has essentially a previous timestamp than the transaction, but that the change has been made to the base data transactionally. However, you would still want your query to see the older value if it happens at the same time. So in this case, both values are valid data.
Yes,
right?
Yes. I mean, that's really setting the stage for what I'm about to say. And yes, in this case, both values are considered valid data. Okay. But in this work that I'm just going to talk about now, we have a way to process that old data right away and pretty much delete it as soon as we don't need it anymore, and not keeping it around for a very long time. So I will talk about this right now. This is our work on snapshot isolation without snapshots that was presented in OSDI in 2020. So this is joint work with Baptiste Lepers and Willis Venopol from University of Sydney and Karan Gupta from Nutanix. And we're going to talk about a very efficient space amplification way to maintain snapshot isolation guarantees. So I also want to make a point about why we would want this. I already hinted about this in the introduction part. So we want to run mixed workloads on the same data set increasingly. So a prime example would be the Internet of Things, where we have a mix of very write-intensive workloads that is continuously recording new sensor data, and analytics-heavy workloads where we would want to read the sensor data to be able to react, for example, for some control, or to run more analytics on our data. This scenario also applies to the cluster management example that I gave, where new data might be incoming, modifications are happening inside the cluster, but we also want to keep to look at the data to run analytics for cluster monitoring at the same time. So this is typically done by using snapshot isolation, which runs analytics on a consistent view of the data. So on a very high level, we can consider snapshot isolation working in this way. So here we have time that goes from the top of the slide to the bottom, and then we have a schedule that runs a long analytics transaction. You can imagine that we want to scan the whole data set to compute something like an average or the top most popular items, or something in that spirit. The data is stored in a key value store that initially holds keys from A to Z with values, as you can see here, 1 to 3, ABC, and so forth. So a long transaction that does analytics is run with this version of the items in its snapshot, or version 0. Now, keys with version number smaller than 0 would belong to the snapshot. And then if another transaction is executed concurrently and say updates key B over here, the data store needs to hold the old version of B, so B0, and the new version of B for the whole duration of the long transaction. Now, this is to ensure that the transaction runs on a consistent view of the data. Now, this seems okay. However, if we imagine lots of these short transactions, or they don't even have to be transactions, they can just be simple updates. If we imagine that we have a write-intensive workload running alongside one of these long analytics transactions, we can soon get into trouble. So an experiment that we ran on an NVMe drive in the lab with 500 gigabytes capacity, and an initial data set starting at 350 gigabytes, shows that the scan on the data set doesn't even progress to 10% before we run out of space due to space amplification caused by all of these concurrent updates happening on the data store. Now, of course, we can have a bigger drive. We don't need to run out of space. We tried the same experiment on a larger drive where the scan actually completed. And at the peak, we measured the space amplification up to 4x. So I want to make a point here that this is especially a dramatic increase in newer drives that have higher write throughput. So on an older, say, an older hard disk, we wouldn't see the same kind of space amplification just because the hard disk cannot sustain that high of a write throughput. Yes, I see a raised hand here.
Yeah, so just to clarify, so I understand this is the key value storage. So is it LSM underneath?
No, I'm going to say what it is soon. It's KVell that we also wrote a few years ago. But what I'm talking about today actually doesn't have to be linked to KVell. So this technique, we showcase it on KVell, as I said, just because the increase, the space amplifications gain are a bit more dramatic because KVell is is optimized for these NVMe drives. But we could use this technique for in-memory databases. We could use it for LSMs. And for SQL-based data stores, it's more general. No, that's what.
Right, but the 4x number that you just
yes, it's on KVell.
Yeah. Okay.
Yeah, this number is for KVell. Yeah. Okay, so this leads us to the question of how we can redesign the snapshot isolation to support writes and analytics at the same time. And this is our main contribution here. So the idea is to increase slightly the snapshot isolation constraints to be able to throw away these old versions right away. And the way we do this is through a new type of analytics we call online commutative processing, which is very similar to online analytics processing, so OLAP, very well-known type of analytics, with two caveats. So in OLCP, we want to be able to process items out of order and to process each item only once, or to read each item only once. I will explain how with these two constraints, we will be able to propagate and delete the old versions immediately. So we reduce the lifespan of unnecessary old versions, at the same time providing the same guarantees as vanilla snapshot isolation. So now I want to make clear that this is an add-on to snapshot isolation, and we can always fall back to vanilla snapshot isolation if the analytics that we want to run may require to break either point 1 or point 2 on this slide. And I will tell you how we do this. So on a very high level, the idea we propose is to propagate and delete the old versions of the items instead of keeping them in the data store. So let's take the previous example where we have a long transaction. Again, we want to scan the entire data set, and this short transaction that's concurrent and wants to update value Z over here. Now, if we want to write a new version of Z and replace the existing value with a new one, we would, instead of keeping both versions of this at the same time, we would propagate the older version of Z to the long transaction, and forcing the transaction to process this element out of order. By process, I mean adding its contribution to computing an average, for example, or a maximum. And we know that Z is only read once by the constraints that we define in the previous slide. So after we process Z, it means that it's safe to delete it right after. So we would only have the new value of Z in the data store, and then the long scan can continue where it left off. In this case, it had processed A already, so it can go on to B. So this is the main nugget behind our technique. So if anything is unclear at this point, I think you should say something now.
So I do have a quick question, and probably you'll explain that anyway, but you also, like the previous slide said, that it's safe to delete Z0 after commit. And I want to understand that a little bit better. So what happens in any of the cases of a rollback of any of the two transactions? So
you mean rollback of the analytics transaction?
The analytics is probably fine. You're just not gonna report the answer. But what if? So if we roll back Z, so if we roll back the short transaction, right? Which means that we need to undo the write. We need to get back Z0, but we can do this through the log, I guess.
So if you have the log, that's where you would find it. In our experiments, we didn't have a write ahead log. So in this case, after you wrote Z1 and you propagated Z0, Z0 is lost. Basically.
Okay, that's fair.
You could add a write ahead log to get around this if you need to. But the whole point is not to keep the old data.
No, I understand. So I guess one other question is, what about in your workload and your assumptions, how frequent was to roll back? That's one other question.
So I can tell about the production workload that we were analyzing from Nutanix. Rollbacks weren't too frequent, but that's because the context was inside the cluster, where failures wouldn't happen too often in these metadata handling. And anyway, if it was metadata handling, there would be a write ahead log.
Makes sense. Makes sense.
Yeah. All right. So let's move on to how we actually implement this in practice. So the OLCP interface is adding a few things to the standard scan or that we see in the key value store. I see the question. Let me just go over the interface and then we can I can go back to it. So we see here 4 parameters for the OLCP interface. And I'm going to start by explaining the scan ranges. So the scan range is basically the range on which we would want to run an OLCP query. So that long analytics that we saw in the previous example. Items in this range are propagated out of order to the analytics transaction, and we need to only go over them once. So we don't keep any items versioning. It's like Z in the previous example. However, if we need to see the items multiple times, or we need to guarantee a stricter ordering, we define a different range in the parameters for LCP, which is basically used as a fallback to vanilla snapshot isolation if we need it. So this is for ordered analytics with versioned items, and it would be the semantics would be similar for vanilla snapshot isolation. The third parameter here is the map function. This is basically incorporating the business logic of the OLCP query. So we have to guarantee that it's called only once per item that's in the scan range. So this map and the scan ranges are connected, and it's a function that takes an item and a payload. Finally, the payload is it's kind of a scratch space for application-specific data. So, for example, if you'd want to store some intermediate computation result, you could do it. You could do it in this payload, right? So I'll take the question now.
Yeah, actually, my question is on the previous slide, and a follow-up to what Manos just asked. So yeah. I'm just trying to wrap my head around. So what happens if the in the absence of a write-ahead log, what happens if the short transaction rolls back?
So if we have the write-ahead log, we would have to go through it and see all of the actions that were done on Z.
Right, but you mentioned that in your experimentation, you did not have any write-ahead log. So I'm just trying to understand that if in absence of a write-ahead log, if a rollback happens to the short transaction, what would happen to the value of Z?
If we didn't have a write-ahead log, then yes. Then this maybe I should have changed this to just say update. So if we don't have a log, then this update wouldn't be a transaction. It would be just a write. So it would be the same semantics of a key value store that has writes, where if you overwrite the value, then the value is lost. Same as in I mean, in hash map or
right. So yeah,
key value store implementation.
Right. So not really a transaction, just a simple key value update.
Yes, I think actually for the remainder of the talk, it would be a better mental model to think about this update as an update and not necessarily as a transaction if there is no write-ahead log. And this is how we ran our experiments.
Right. Makes sense. Just wanted to clarify that.
Yeah.
Yes.
Yeah. No, that's it's all very good questions. And I'm happy you asked something, because this really, if you miss this part, then what I'm going to say next doesn't make that much sense. So
exactly. Yeah.
It's very good. Okay. So I also want to make a quick point about whether this new model is practical, right? And it may seem restrictive compared to traditional OLAP. However, we found that it can be applied in quite a broad range of analytics. So for transparency, the way this started was from MapReduce style analytics. So we are basically looking at this cluster monitoring workload where the a long scan would run alongside other cluster management operations that were mostly writes. And this was implemented in a MapReduce style job. The long scan was implemented like that. And the problem was that this query was facing was large write amplification and space amplification, which ended up in having to do some workarounds with the analytics scan specifically, and I won't get into that. So this style of OLCP analytics maps really well to the MapReduce interface, and I hope you can see this just by the way that the interface is worded in the previous slide. However, we can also apply it to other more classic style of analytics. So in relational analytics, for aggregate functions where the order doesn't matter and we only need to look at each item once, such as simple counts, sums, group bys, etc., this model works very well with no space amplification. Even joins, where we would sometimes need the ordering depending on how the join is implemented. So if we have, for example, a hash join, then we wouldn't need the ordering. That falls a bit better in this OLCP model. But if we would have a join where the order is necessary, then there would have to be a bit more adaptation of the query to be able to save some space with the scan ranges. This is we tried. You can look in the paper for more details. We tried to adapt all of the TPCH queries, so the 22 queries, and we found a way to adapt all of them to KVell+. But some of them were friendlier than others, let's say, and some of them would have a lot more gains in space amplification than others. Another interesting example where this could be applied is in multidimensional analytics. So if we think of databases that are working on these multidimensional cubes, the way the cubes are formed is typically by pulling from different kinds of relational databases and creating this special data format. So we think a nice way to extract the data from the relational databases with low space amplification could be through one of these OLCP queries. So the space is quite broad, even with these two constraints of out of order processing and reading exactly once. I'd like to quickly skip now and how we implemented the OLCP on top of KVell. So a brief crash course on KVell. This is a key value store optimized for NVMe drives. And, it's open source. You can check it out here. The three main principles in KVell are not sorting data on disk. And this we can do because of the guarantees provided by fast drives and efficient random writes, basically. That's what allows us to keep the data unsorted on disk. We have an ordered in-memory index, however, for running scans. And we do sharding to increase parallelism. Now, here, I wanted to make the point that we use KVell just because we can see really the difference that it can make for space amplification with a key value store that is optimized for writes and fast drives. But the technique can be applied to other databases as well. So the design of KVell has these three simple principles. We keep the data unsorted on disk. So the design is similar to an in-memory allocator, really. We have different files that each keep different classes of item sizes. So in this example, we have 3 files with 3 different data sizes. File 1 has smaller items and file 3 has bigger items. If we want to add an element to KVell, we would find the appropriate size class, and we will just add the entry in the first free slot. If we want to remove an element, we would have to find it in the index, find the slot, and just simply delete that element, and the spot is there to reuse. So it's a very simple model, and we did this in order to put as little pressure as possible on the CPU. And this is another talk, but in case you were curious, this is why it's so simple. We do need to keep track, though, of the elements, so we do need an index. And this is a purely in-memory index, and it's rebuilt every time the database starts again. So we would need to do a sweep through the dataset and recreate this index. The index is a tree. It's a concurrent. Well, it doesn't really matter that it's concurrent because we shard, but it's a concurrent tree where keys are indexed by prefix, and each index contains index entry contains a reference to the file and the index of the element inside the file. Briefly, also, we shard to be able to have hyperparallelism. In this example here, we have 3 worker threads all in the same machine, each looking at the third of the key space. And what this means is that each worker has their own indexes and their own files. So minimal locking is necessary only when we would put back together the results of a scan. So that's how KVell can be so efficient for writes. So now that you have an idea of how KVell works under the hood, I'm going to tell you how we process the elements exactly once. We do this with the 2 simple techniques. First, we need to track the snapshot timestamp, and then we need to track the last processed item. And let me show you why we need each of these. Now let's go back to the previous example where we have a long transaction and the short update. The snapshot timestamp that we track is 0. Now let's assume that we want to update C. So as before, we propagate C0, we process it out of order, we continue the processing in the analytics transaction with B. However, let's say that C is a hot item and it will get updated again. Now, because the old item, so the item that was already in the database has a timestamp that is older than our snapshot timestamp, we don't propagate, and we can just immediately replace C2 with C1 with the new version C2. So tracking the timestamp is needed to avoid processing the same element twice. We also need to track the last processed item for similar reasons. So assume again the same example where we have the scan running and we want to update A this time. However, we can say that we can assume that A was already processed by the scan, then B, and then we would want to update A. Now here, even if A's timestamp is the same as the snapshot timestamp, normally we would want to propagate it. However, we know that the last processed item in order in the database was B. So in this case, we would have to not propagate A. I see, Manos, you have a question here. Yeah.
Yes. So just to understand, because I was thinking also before, what type of metadata you need to store for that? Because in the beginning I was thinking, okay, so we need to know every key, whether it is going to be used by an analytical query, right? So okay, so what you're saying here that okay, we need the timestamp and the last processed. The last process comes from the assumption that there is a unique order of processing in the transaction.
Yes.
Which of course we circumvent by doing out of order when you use OLCP. Okay. But then I'm not sure I understand fully whether we need more metadata to know when to trigger something. So how do I know that? So when you are going, if we forget this transaction on the left-hand side, it exists, but we don't know it. But I don't know why we know it exists, right? So we have the write A update, the update of A, and that changes A0 to A1. So how do I know at that point that I have to propagate A0?
So it's a really good question. And I'm going to kind of sketch the correctness here if we have kind of a more elaborate explanation in the paper. But in this case, if we want to update an element, right, there are two options. Either in the longer analytics, we keep track of the analytics first of all. So we have a table in the metadata KVell that knows the scan ranges and the point ranges of all the analytics that are running in the system. In this case, there's only one. So we would know the scan ranges and we would know the point ranges. Now,
essentially, I think, by the way, that was my question. Essentially, you have some metadata. I don't know what exactly is the data structure, but you have some metadata, and then every time you make an update on a key, you're going to see in this metadata, does this key correspond to a range that is now being serviced in a query?
Yes. So we would have to check that A, in this case, is in the scan range of this analytics transaction, because otherwise, if it was, say, in the point range, we would have to keep all the versions actually, and we wouldn't have to do the propagation. We can only propagate because we know we can delete the old version immediately, and that it's safe. So yes, indeed, there we would have to check that that it's safe. Yeah. All right. So now quickly, I would like to show some results of the performance of this snapshot isolation mechanism. I'm going to use the standard YCSB benchmark, just so we all know what we're talking about. Yeah, we run this in a system with 4 cores and an Intel Optane drive, the one that I was mentioning in the previous experiment that ran out of space. And for the competitors, we have the vanilla snapshot isolation in KVell. The implementation is inspired by the RocksDB snapshot isolation, but we don't compare to RocksDB for the space amplification experiments just because it's not an apples to apples comparison. So we really wanted to port the same snapshot isolation mechanism onto the same baseline. I am going to show some RocksDB experiments though, just for you to have a sense of how KVell works relative to RocksDB. So this is the full YCSB benchmark. You can see that especially for write-intensive workloads, so YCSB A and F, KVell is much faster. And this is why we can see this more dramatic increase of space amplification with the vanilla snapshot isolation in KVell and not so much in RocksDB. Also for scans, KVell has a similar performance to RocksDB, which is actually keeping all of the data in sorted order, and it's very good for range scans. Now in this YCSB-E experiment, since it's scan dominated and the scans are short, we can't really see this space amplification effect from the YCSB benchmark. So what we did to trigger it was to emulate a new workload synthetically that runs the update heavy workload, so YCSB-A, in addition to a long scan that's similar to what we would have in YCSB-E. And this is very close to the kinds of workloads that we saw at Nutanix that combine a write heavy transaction and a write heavy workload and an analytics transaction. So this is the plot that I showed before with the time on the x-axis and number of old item versions in the millions for KVell with vanilla snapshot isolation. It's the scan that didn't manage to finish because we ran out of space. At the same time, in the OLCP KVell version, we can delete items immediately, so we have almost no space amplification for this kind of workload. Another interesting side effect for this item propagation is that the throughput of the scan increases, and this is simply because the propagated items are already in memory, so they don't need to get fetched from this. This is kind of a surprising thing because we weren't really trying to optimize for throughput, but it happened as we were doing these propagations. So this is it for KVell. So we have this new OLCP type of transaction that avoids space amplification. And it fits many practical analytics and is efficient. So I would, since we had many questions, I would like to go to the learned index part now, and maybe keep the rest of the questions for the discussion session that's planned after the talk, if that's okay with everyone.
Yes, that's fine.
So here, the second part of the talk is a more ongoing work that where we're taking the first steps in this learned index world. And it started with the third space amplification problem, if you remember from the beginning of the talk, that we have large indexes, especially for small items. So one thing we wanted to explore was, what about replacing this B tree that we are using in KVell with something that's a bit more space efficient, like a learned index. And this opened up a whole array of interesting research questions. Today, I'm going to talk to you about one of them, which we recently published in a workshop. So it's a learned index that aims to decrease tail latency in write-heavy workloads. And this is joint work with two of my undergraduate students, Yong Zhang and Xinran Xiong from McGill. So this part of the work addresses the index, the growing index issue. If you remember from KVell, we have a tree that keeps track of the keys. And especially with large data set and small items, the ratio of metadata to data isn't very good. So we could have the size of the metadata being almost as large as the data for small key value pairs like 8 or 16 bytes. As I was saying, for good performance, the indexes need to be fully in memory. However, we have a number of problems that cause index bloat. So we can have this bad ratio of index to data for small items. We might have even the height of the index itself that adds even more metadata. This isn't such a big problem because it's logarithmic in the number of keys, but it still contributes for very large data sets. And finally, maybe we don't just want one index, maybe we want multiple indexes to be able to run multiple types of analytics on the same data set. So all of this leads to memory consumption for the metadata. So our idea was to use learned indexes instead of trees or skiplists. So learned indexes are a new way of indexing data proposed by Tim Kraska in 2018. And the idea is to have, instead of a classical data structure, is to have a model that predicts the position of a given key inside a sorted array. So you can basically model the probability that a key is at a certain spot in the array. So in this formula that's very simplified here, position is the position estimate. F of key is the cumulative distribution function for the data, and this is a learned function. That's why these are called learn indexes. And the n is the total number of keys. So intuitively, visually, if this blue line is the key distribution, the learned key distribution would be this orange line, given that we have a linear estimator. In practice, though, because distributions are more complicated than straight lines, we use a piecewise composition of linear estimators. There has been work on using other types of estimators, but in practice, we find that the linear ones are good enough and also very fast compared to other types of models. So this is what we went for. So in theory, the learned indexes would be perfect, right? They are, the height of the index would just be proportional to the number of models that we need to estimate the data distribution. The models occupy order of magnitude less memory than the B-tree, so at least that's what that's what was shown in the original Learn Index paper, and that would allow us to cache multiple types of indexes, so run more interesting analytics on our data. However, we found that Learn indexes can't really be used out of the box, and the biggest issue was that they were designed for static data sets. And even the initial design proposed in 2018 was for a read-only index. There has been work recently that augments learned indexes to be able to support updates. However, as we were trying several of these indexes, we found out that there is still very high tail latency in write-heavy scenarios, and there is still quite expensive synchronization for concurrent updates. Today I want to show you what we did to mitigate the tail latency in write-heavy scenarios in TOE. So to tell you where tail latency comes from, so for reads, it's very easy. The models are queried, and latency for reads in general is very low, in the order of a few microseconds. The high tail latency comes from write requests. And, to be able to explain to you where this comes from, I need to tell you where the models, how the learned indexes deal with the writes. So in Alex, as a state-of-the-art learned index, we have these gapped arrays to accommodate updates. So new elements would just fit into the gaps. And this is very similar to leaving extra space in leaf nodes for B-trees. That's the whole idea. However, as you know from B-trees, sometimes nodes run out of space. So here come the structural modifications for these gapped arrays. If the array gets too full, we would need to expand it. But since we still need to keep true to the model's data distribution, we will need to copy the data at the right place, or at least to move around some pointers. So this operation is quite expensive. The second thing that we can do is a split. So say we have one of these bigger arrays that corresponds to M2. However, we can notice that some of the items follow a different distribution than the rest of the items. So in this case, this is a good candidate for a node split, which also entails some data movement and some retraining as well of the model. Because instead of one model, we would now have a different layer in the hierarchy. The third structural modification operation is model retraining, which just means that if the workload evolves over time, the key distribution might look differently. So we would just need to adapt the models to reflect the new reality of the key distribution. To understand where the latency comes from, we wanted to see how each of these structural operations associated to writes impacts the tail latency. And we measured it in Alex. And we actually found something quite surprising. We were expecting that the model retrains would dominate the cost by far. However, it turns out that linear models are very cheap to retrain. And most of the time is spent in expansions and splits. So since the data movement cost dominates the tail latency, this is really a very good fit for a systems problem. And we set out to solve this issue. So Tone is built on top of Alex. It's using pretty much all of the same mechanisms that Alex used, apart from this secondary gapped array that we add. So the idea in Tone is to do the data movement outside of the critical path to be able to bring the latency down. So that's why we introduced a two-level gapped array. The secondary array is used to absorb the updates during the structural modifications. So that means that the structural modifications would happen in the background and less often. And I'll show you why by focusing on this node here on M3. So let's say we have M3, we have a relatively empty gapped array, bursts of writes come at M3, we have a write-heavy workload. Okay. Maybe now there's another element that the model predicts should be in an occupied slot in the primary gapped array. And this is where we know that we are having some issues. So we would allocate a new secondary array that uses the same model as M3, and we place the new item here. At the same time, we say, okay, this node is getting too full, we might need to reassess. So we might need to do a structural modification. The tree will decide if it will be a retrain, a merge, or a split. So we let the Tone algorithm decide what to do, but we just trigger it in a separate thread in the background. So this leads, this very simple trick, systems trick, leads to pretty important improvements in tail latency. So this plot shows the write latency breakdown again for Tone and for Alex. And we can see that even if Tone spends a bit more time expanding and merging in the background, overall the tail latency goes down significantly compared to the tail latency in Tone. And this is under a write-heavy workload that's relatively static. So we wanted to see what happens if things are pushed a bit more. This is why we synthetically generated the workload where the workload was write-heavy, skewed, and the skew would evolve over time. So you can imagine the first n items are hot for the first x seconds, and then the skew moves towards the next n items. And here is where we saw that Tone really shines. So the plot on the left shows a timeline of the tail latency for Tone in orange and Alex in yellow, and throughput for Tone and Alex. So we can see that the Tone latency is low and steady, while the Alex latency peaks even to 80 microseconds, and the throughput is on par. So we don't lose much. We don't lose much there. This is just the first step, though. So in the future, we want to integrate this in KVell as an index and run some real measurements there. We also want to adapt these indexes for data that is in persistent storage. So for now, these indexes are purely in-memory data structures. We know there will be some work there to be able to do that efficiently. And we want to integrate better concurrency control for this data structure. Thank you for bearing with me. To conclude, today I talked about space amplification that is preventing us from running long analytics alongside write-heavy workloads. And this is especially true on fast drives. I would like to thank all of my students, especially Shinran and Yong, who contributed to the work on Tone, and my KVell and KVell Plus co-authors again. Everything is open source. Please check out our papers and our code if you're interested. And let me know if you have any questions. Thank you.
Thank you. Let's thank our speaker. Thank you so much for a great talk.